Hello and welcome back to my channel. Today we're going to be talking about Taylor polynomials. So Taylor polynomials are what you end up hearing a lot about, or Taylor series, which is something we're going to talk about a little later when we hear about Unit 10 of sequences and series. So let's talk about them. Consider the function f of x is equal to e to the x. Without technology, what is e to the 0.1 power? So far what we've learned is that in order to find something that is about the same, we need to use a tangent line approximation. So we want to find the tangent line for this function at x equals 0. So the first thing that I need is f of 0 to get my xy point. So we have e to the 0 power. E to the 0 power happens to be 1. And then we need to do the derivative. So we have f prime of x is equal to e to the x power. And we need to plug in 0 so we can get our slope. It is also going to equal 1. So we're going to plug it into either our point slope form or y equals mx plus b. Thankfully, either one is really easy because we are given the y-intercept. So if we go with y minus y1 equals x times x minus x1, which works for any situation, we have y minus y1, which is 1, equals our slope times x minus 0. If we simplify this, then it is that, which looks gross, so we would probably say y equals x minus 1 or 1x plus 1. What am I thinking? So we would get something like this. For what we're going to be doing, I'm going to rewrite this in a weird way for what we're used to. We're going to write it as 1 plus x. The reason I'm going to be doing this is because of what we have later on. Instead of ordering our terms from highest exponent to lowest, for our x values, we're going to do the opposite. So now we'll approximate that value e to the 0.1. So e to the 0.1 is about 1 plus x, so we have 1 plus 0.1, which is equal to 1.1. If I actually put this into a calculator, e to the 0.1 is equal to about 1.105. So looking at these two things, that value is super close to the value that we wanted. So a Taylor polynomial is an approximation of a function using polynomial functions added together. So this tangent line that we've been dealing with, this is a Taylor polynomial. Realistically, it's an example of a Taylor polynomial. So there's a couple things that we need to know about Taylor polynomials to kind of help us out. So things that every Taylor polynomial has. First thing, it has a center. Our center is going to be denoted by c a lot of the times in our equations. So this is going to have a variable of c. So our polynomial centered at or expanded about, those are going to mean the same things, x equals c. Our example is it's centered at 0. And this is a really important one to know because when a polynomial is centered at 0, we actually call it a Maclaurin polynomial or Maclaurin polynomial. It's a Taylor polynomial with a specific condition. So if you hear the words Maclaurin or you see the word Maclaurin like we have here, that just means our center is 0. The degree, which is our biggest exponent in this given problem, our degree was 1 because it was a linear approximation, so this was a first degree polynomial. So we have n as our variable here. N is always going to be that biggest exponent. We have our function. In our last one, it was e to the x. This is going to be our f of x. So we want that. And then notation. So Taylor polynomials are denoted as P, capital P sub n of x or T sub n of x. P, I'm assuming for polynomial, T for Taylor. And then the last thing is we want to write our terms in ascending order. So the opposite of what we're used to, we want to start with a non-x value and then work our way up. So if we are centered at C, we might have P sub n of x is equal to our first term plus our second term times x minus c plus our a sub 2, which would technically be our third term, x minus c squared. And this is going to follow this pattern. We're going to keep multiplying some coefficient that we may or may not know about times this x minus our center to the power of whatever a sub we're on. And that degree increases every single time until we get to whatever our n is to get a sub n minus c to the nth power. On the other hand, if we're centered at 0, it's going to look exactly the same, except for we don't have x minus c, so we just get p sub n is equal to a sub 0 plus a sub 1 x plus a sub 2 x squared all the way until we get to a sub n, x to the n power. So a lot of this right here is kind of just the things that we need for a Taylor polynomial. And we're going to dive more into what these would look like, things like that, in a little bit.